So this is ECE 343 Signals and Systems. We're going to do part 5 of chapter 2. This should wrap up chapter 2. So last time we had talked about convolution and convolution properties. Today we're going to just look at a few remaining details, a few last topics of chapter 2. So the first thing I'd like to look at is one of the neatest properties of a linear time invariant system, and that's how it responds to a complex exponential input. So let's go ahead and look at the LTIC system response to this input e to the st. This complex exponential is something you should be familiar with. For the time being, we're going to go ahead and let it be a frequency s, where s could potentially be a complex number. We had defined this as our basic unit of frequency earlier in the semester, back when we were in the background chapter. So if we go ahead and we apply that e to the st input into our system that has some impulse response h of t, right? We know that as long as that system was linear time invariant, the output is just going to be that input e to the st convolved with the unit impulse response. We also know that convolution, from the properties we talked about last time, is not affected by interchanging the order of the convolution, so I can do that as h of t convolved with e to the st. And then I'm going to go ahead and write by definition that convolution in its integral form. So h convolved with e to the st is just going to be an integral minus infinity to infinity of our impulse response, h of tau now, right? And then we have e to the st minus tau, so we're going to flip and shift the input. We chose this particular order just because it is the most direct way to get to the result that I'm looking for. That exponential, right, has a sum of terms up there, so I can break it up into a product of two exponentials. That's just the simple rules of exponentiation. So the next step down, I just go ahead and do that. I break that exponential into a product to two exponentials. One of those exponentials, right, this first one, the e to the st, is not a function of the variable of integration, and as a result, it can be pulled outside the integral. So I can pull that e to the st out, and then I'm left with just a single term, right? This integral minus infinity to infinity of h tau e to the minus s tau d tau. You don't see any t's in there whatsoever. So that particular term is completely independent of that variable t. There is no dependence on time. We're going to go ahead and call that something else, and it is a function of the input frequency s. So we're going to make it a function of s. Let's call it cap h of s. For those of you who remember back in your circuits days, this should look like a familiar expression. In fact, we know this is the Laplace transform, right, of our unit impulse response. So this is giving us some kind of hints in this class that this thing called the Laplace transform is going to have direct relevance to the kinds of things we're studying with understanding systems and signals. So we go ahead and we call that constant with respect to time, but not a constant with respect to the frequency variable. But we take that constant and we call it h of s, and then we see that the output, right, the output of our system in response to that complex exponential input is just the same complex exponential, right? And it's getting modified by that function of s, that constant, right? This changes the overall gain or maybe phase of that exponential by an amount that's related to h of s. I don't know. This is just super cool to me. This idea that I can put a waveform into a system and that it comes out undistorted in shape. Exponentials are really the only kind of signal that are guaranteed to pass undistorted in shape through linear time invariant continuous systems. So in other words, if I have an exponential input, right, something of the form e to the st, that's our base unit of frequency, we get that exact same signal out, e to the st, right, same exponential output being scaled by some simple quantity, which happens to be the Laplace transform of the unit impulse response, that h of s. We're also going to call that h of s the system function or the transfer function. We'll get more on that when we get to chapter 4 and we talk about the Laplace transform. So exponential in, exponential out. This is not something that happens for most inputs. You put most type of inputs into a linear time invariant system. Let's say you put a square pulse in, for example. That square pulse is almost always going to come out not looking like a square pulse. You put in a triangle function, it's not going to come out looking like a triangle. You put in almost any shaped function, and it gets shape distortion of some sort. because most inputs to those systems cannot pass through undistorted in shape. It's really only those complex exponentials that do so. Mathematicians have a name for this. They call that signal e to the st an eigenfunction of this system. So it's a characteristic function of this system, and they just have that really special property. I know that we talked back in the background chapter, part of the reason we spent so much time with the complex exponential was just saying that exponentials were really necessary for us to be able to fully understand and proceed with systems. And here we're getting a good indication of that. I'd like you to also think about just this idea of the operation now that we can use in order to find the output in response to an exponential input. We know for a generic input, right, to find the output, we have to convolve the input with the unit impulse response. But in this case of an exponential, right, in the case of an exponential, you really don't need the convolution. You just need multiplication. You just take that exponential and you multiply it by the transfer function, h of s. That is awesome, right? Get rid of that convolution operation, which can be kind of tricky, and we turn it into multiplication. In fact, as we'll find out when we get to chapter 4 and we formally talk about the Laplace transform, this is one of the powers of transform domain analysis. It can turn difficult operations in the time domain, such as convolution, into much simpler operations in the transform domain. Convolution, for example, becomes multiplication. Differential equations, which are hard to solve in the time domain, become algebraic equations. So there really is some interest in being able to look forward to this idea of doing transform domain analysis. A very short one that doesn't take a lot of explanation. Last chapter, we talked about a bunch of system properties. Our method for demonstrating particular system properties was somewhat ad hoc. It wasn't always obvious on how you might show something. But think about this. We know that for a linear time invariant system, its output in response to an input is fully characterized by the unit impulse response. How do I know that? I know that because the output is just the input convolved with the unit impulse response. We derive that. So as long as you have the unit impulse response, you know everything you need to know about that system's input-output behavior. It stands to reason then, right, that we should be able to tell quite a bit about a system, right, just from its unit impulse response. If that unit impulse response completely characterizes input-output behavior, we should be able to tell some of those system properties. One of the really easy ones to tell here is whether a system is causal. Think about the input of a delta function. So if I take a look at an input function here, and I'm going to go ahead and just draw it in red, if I put in a delta into a system, right, so I'm going to go ahead and put that delta into my system, something like that. And then what comes out? Well, we know what comes out is the unit impulse response, and maybe it looks something like that. Maybe it looks like some sort of kind of wonky curve like that. So we had delta in and we had h coming out. When is the first time that the input is non-zero? Well, it's first non-zero at 0. If the system is causal, right, if it can't respond to future inputs, it can't respond to that delta function until 0 and later, right? So a causal system, if we wanted to just summarize that in a really simple, easy to test manner, is we'd say if the unit impulse response is 0 for all times less than 0, then we can conclude that the system is causal, right? So what are we going to look for? We are going to look at that unit impulse response h, and we're just going to make sure it is 0 for all times 0 and earlier, right? Because we know that causal systems can't respond until the input has occurred, and at least for the unit impulse input, right, that input occurs at 0. And once we know that, we know how the system responds to anything, right? And so very simple test for causality. If you know a linear time invariant system's impulse response, you can immediately determine whether or not it's causal. Let's also talk about stability. Stability turns out to be one of those ones back in chapter 1 that was a little bit tricky or challenging to necessarily make assessments of stability. And we are going to be able to just make much quicker assessments of stability now that we have some mathematics associated with these constant coefficient linear differential equations and all this stuff like zero input and zero state response. We're going to further refine our idea of stability. We're going to give 2 forms of stability that you can look at. We had talked at the last part of chapter 1 about this difference in internal and external descriptions of a system. So an external description, you just can throw something on the input port and you see what comes out, and you try to figure out system behavior by looking at how inputs go to outputs. Internal system descriptions, right? We can actually take a look inside and we can see what kind of pieces are where. Well, we know from our study of the zero input response that the way we got a zero input response was by having full access to the system's differential equation description. That's an internal kind of description. Furthermore, we know that that zero input response, we're going to look at the case of unique roots. If you didn't have unique roots, we know how to handle them. We would just get additional powers of t on some of those modes, like a t squared, and so forth. For right now, it doesn't do anything but distract us if we consider those repeated cases. So we'll just stick with the unique root cases. So in the unique root cases, we know that the zero input response is just what? It's a linear combination of those natural modes. So it's some sum over n terms. N is the order of the system, some coefficients ci, right, which are determined by initial conditions, and then the e to the lambda it. Those are the time varying pieces that come out. And the lambda I, right, tells us the shape of those pieces, and that comes from the characteristic polynomial q. If we think about this system, right, if you stuff energy into a system and it's stable, right, it should not take that energy and cause it to grow without bound. It should take that energy and at very worst just maintain the energy, right? But most likely should let that energy dissipate off in a nice kind of controlled way. So we can start thinking about things like internal stability, and this is the strong form of stability. If you know internal stability, you really know everything you need to know about stability. External is not quite as complete. We talked about that too back in chapter 1 when we talked about things like unobservable or uncontrollable systems. But right now we're looking at internal. So internal stability, we just don't want those modes to blow up. When we put energy in the system, right? Energy in the system is accessing all those internal parts of the system. We just don't want that energy to go flying off to infinity. Well, this is really easy to determine. We just need to make sure that those e to the lambda its, right, don't grow without bound. So the zero input response reflects the system's internal structure. For assessing internal stability, which we also call asymptotic stability, we just need to look at those lambda i's and make sure that those corresponding characteristic modes, e to the lambda it, decay. Well, that's pretty easy to determine as well. If the real part of lambda I is in the left half plane, so the real part of I is less than 0, right? Then we're going to have an exponential decaying envelope on that mode, and that is energy dissipating down to 0 in a nice and controlled way. We could have the real part of lambda I being on the imaginary axis, so the real part of lambda I being equal to 0, in which case the envelope of our terms is neither going to grow nor decay, as long as they weren't repeated. That's just on the boundary of stability. If I had the real part of lambda being greater than 0, something like let's say lambda was equal to 1, right? If I thought about something like lambda equaling 1, we would get an e to the t, and what does e to the t look like? That's that exponential growth. We know we'd be in deep trouble. So some different cases. We said lambda like being in the left half plane, that would be like lambda equaling -1. That would be a mode like this, decaying, right? You could have something like lambda equaling 0, right? That's e to the 0, that's just a constant. So that's neither growing nor decaying. It's right on that boundary of stability. And we had something like lambda equaling 1, that gave us like an e to the t that was growing. So we can get this idea that really, when it comes to stability, we just need to see where the real part of our root is. If all of our roots have the real part less than 0, then the system is asymptotically stable because every single mode decays away in a nice, simple pattern. If we look at marginal stability, or what is called that boundary of stability, we need to have some lambda, and it has to be unrepeated, where its real part is equal to 0. That means an envelope that neither decays nor grows. And in any other ones that might not be on that imaginary axis would have to be left half plane. They'd have to have the real part of lambda I being less than 0. We'll show some examples of all of these. Unstable is all other cases. So any kind of growth that is unbounded would give us an unstable system. We could see that with the real part of lambda for any one of them, right, being greater than 0, that one mode would blow up. And one mode is all it takes, right? It only takes one bad apple to spoil the whole barrel. If you have one mode that is unstable and the rest are stable, that unstable one kills the good behavior of all, right? You can also think about there's that sort of tricky condition where you might have roots that are repeated on the imaginary axis. We'll look at this example in a second. Remember what happens when you repeat a root. New modes come in. And so that new mode would be a t times something. Well, a t times an envelope that doesn't decay all of a sudden now becomes linearly growing. And so again, that would be an unstable condition. So let's take a quick look at some examples of these systems. What I've done in this particular case is I've gone ahead and drawn some pole plots, okay, some plots that plot out the characteristic roots of our system. So I have an entire row up on top that shows some first order systems, so single pole, except for the third column. That's where I'm going to do some doubling. And these ones are all real, so maybe that would have been more correct just to say that I have all real roots on this top one. On the bottom one, I'm going to go ahead and look at some conjugate pairs. And we know that when we get some imaginary part of our lambdas, now we're going to get some oscillation, right? Because e to the j something t has an oscillatory component. Let's take a look at the first diagram that I gave. That's this one sitting over here where I have a single root off on the left half plane, real root. We'd already kind of got a hint on that. That might be like -1. That gives us a decaying exponential, e to the minus t. That's that line in blue directly beneath the graph, right? So we get that curve going down in an exponential way, right? Nice and stable system. That's why I put the green check arrow over there, because you stuff energy into the system and it bleeds that energy away and heads off to zero. If we look below, right, and we take two roots that are in a conjugate pairing, right, the real part of those roots is still negative. This might be the roots at -1 plus or minus j. The -1 part causes the overall modes to still have that e to the minus t decay, which is why the curve in red above, right, that oscillatory curve, still tracks that exponential curve because they share the same real part, right? They share that real part of lambda being equal to -1, for example. The fact that I've got the roots off of the real axis indicates some oscillation going on there as well. So we get an oscillatory component that is exponentially decaying, that red curve. Again, this is still a stable condition because you stuff energy into the system and it bleeds away, right? It doesn't cause any kind of exponential growth. If I move that root, right? If I move that root towards the omega axis, right? Like this next one is, I took that single root, that single real root, and I moved it over until it was right on the omega axis. It turns out this is in the origin. This is a root lambda equaling 0. E to the 0t is just a constant, right? And that's why I get a constant, that blue line corresponding to that blue root, the mode, is just a constant. This is that boundary of stability. If we moved it a little to the left, it would exponentially decay, right? But when we get it right on that omega axis, it's at that boundary point between decay and growth. It just holds the value. This is on the edge of stability, and they use a special term for that. They just call it marginal stability. We could do the same thing for the pair of roots, right? Now there's no exponential decay, so the envelope for that oscillation doesn't decay, right? It just sits there and oscillates like a sinusoid. In fact, this is exactly the kind of characteristic roots that we'd expect for a system that was supposed to function as an oscillator. If you did a CL, a capacitor inductor circuit, just put a capacitor in a loop with an inductor, nothing else, and they were ideal, they would behave exactly this way. You should have seen that in circuits. They would just cause an oscillatory output, a cosine output that neither decayed nor growed. Marginal stability. I'm going to go over to the very right one. If I kept moving that root over further to the right, so here I've moved that real root over into the right half plate, maybe it's to a value 1, that would be like that e to the t that's exponentially growing, that blue line exponentially growing. There's where you put energy into the system, and it just keeps rebuilding and building and growing, and it flies off to infinity, and bad things happen. Circuit boards melt, entire planets collapse, right? So that instability is definitely something that we want to avoid. If I had conjugate roots in there, they're still bound by that exponential growth, which is why the red curve above there, that oscillatory curve, still is growing exponentially. It just has some oscillations in it because the imaginary part of the root, right, is not 0. That imaginary part tells us something about the rate of oscillation. By the way, if I had just changed this, and let me think about this. Let's go ahead and put it maybe in green. What would happen differently if I put a couple of poles out there? Same real part, like 1, right? Real part of lambda is still 1. But now I've made the imaginary part larger in magnitude. What does that mean? The further I get away from the real axis, the faster is the oscillations, okay? So the oscillatory frequency depends on how far, right, you're traveling vertically. So in this particular case, I've moved a good distance from where that red pair of roots were located. And so if I looked at that one, it would just go faster, right? But it would still have that same exponential envelope. Both of these cases are unstable, right? Both of these cases that we just did are unstable. The weird, quirky one, the one that you could look maybe first and think, maybe that should be marginally stable because you don't see any poles in the right half plane, is when we get poles that are on the omega axis, but they are repeated. Let's take a look at this first one. So this first one is a lot like the one to its left, right? I just repeated one of the roots. What happens when I repeat the root? I get a couple of modes in there, right? I get a couple of modes. The first one, the lambda equaling 0, the one that's just all by itself, has an e to the 0t, which is just a constant, right? But what happens when I repeat a root? Then I get a t, e to the root, 0t in this case, and that is t. And that t term, right, in this particular case is going to cause that overall output to sit there and grow without bounds. We see that grows as a function of t. So when I repeat on the omega axis, right, that t pattern on there makes something that was flat before now grow without bound. That's an unstable condition. We can do the same thing. The last one down there is just repeated roots that now have an imaginary component. It's the same thing. I'm going to have linear growth on there, but it's also going to have an oscillation in there. You might wonder why it is that doing something like this, if I go back to the very first plot and I look at something like that and I repeat that guy, right? So I have a repeated root in there. What are the modes in there? I might have something like an e to the minus t, and I might have a t e to the minus t, something like that. And you might worry about that t term out front, right? Because t grows, but we also know e to the minus t decays. And the question then becomes, who wins? And it turns out that exponentials always win. Exponentials decay, this exponential decay, is a faster decay than any kind of polynomial growth. That's something you can easily show if you just do a Taylor series expansion of that exponential. You'll see it has all polynomial terms included. And so that exponential decay will win every single time over that polynomial growth. As a result, even though it might grow initially a little bit, it wouldn't be atypical in this case. If you looked at those modes together, maybe they'd do this, they'd grow for a little bit, but then they're going to come back out and decay. Eventually, that exponential decay will win. That is still a stable condition, okay? So if all of your roots are left half plane, no problem, stable. If most of them are left half plane, but a few unrepeated ones are on the omega axis, we have marginal stability. Any other condition is going to be unstable. We also had talked, and this was back in chapter 1, about the external stability measure, this idea of bounded input, bounded output stability. My guess is that most people really didn't like trying to find ways to demonstrate a system was BIBO or externally stable. That wasn't necessarily a very simple process. You needed to do some thinking about the system, and you didn't necessarily have a straightforward single one-size-fits-all way of demonstrating that. In the case that we have these linear time invariant continuous systems described by constant coefficient linear differential equations, for which we know that we have an impulse response, and that impulse response captures the character of the system, we can end up determining BIBO stability in a very straightforward procedure. Let's look at it in its math. What is BIBO stability trying to do? It's saying is the amplitude of the output, is the absolute value of y, right? Is it a finite number? So I'm showing the other end very far away. We want to know, is the output bounded if the input is known to be bounded, that the input's magnitude is always less than some finite number. I called it mx here. Okay, so what I'm going to do is I'm just going to work with this in a directly mathematical way. And I'm able to do that mathematical consideration of this because I now have a mathematical expression, right, that relates output to input through this thing called the unit impulse response. So I know the magnitude of yt is just a magnitude of what is yt? Well, it's the convolution integral. So I have the magnitude of the integral h of tau x of t minus tau d tau. A magnitude of a sum, and an integral is just a sum, is always less than or equal to the sum, integral in this case, of the magnitude. So I get the magnitude terms in there. This is just application of a mathematical property, a mathematical piece called the triangle inequality, something you should have seen before. What do I also know? I know that the magnitude, right, of that input by constraint, when we talk bounded input, that's the given, right? And then we're checking, is the output bounded? So we know that that magnitude of x is always less than or equal to some finite number. So this entire expression that I had, right, this whole expression so far is going to be less than or equal to, plug in mx for that magnitude x, and I can pull it out because it's not a function of the variable of integration, and then I'm left with an integral of absolute value h tau d tau. We want to know, is this guy finite? Well, what could I do here? I could divide this left side by mx, and I could divide this right side by mx. Infinity divided by a finite number is still infinity. So my test here could be something like the following. If, right, if my impulse response function, h of tau, is absolutely integrable, which means this integral here, right, is a finite number, then I know that my output magnitude is also bounded. It's also finite. So our test for BIBO stability becomes very direct. We just look at the integral, the absolute value of h of tau, and see if it is a finite number. Is h of t absolutely integrable? If it is, it's BIBO stable. If it is not, it's BIBO unstable. I'd encourage you to take a quick look at some point in the book. The book will also talk about connections between internal and external stability. Turns out if you have internal stability, the asymptotic stability, you can infer what is the external stability. You can't go the other direction, but if you know internal stability, you can get the stability for an external measure. Okay, last few bit of topics. This really focuses on some intuitions about system behaviors. In particular, we're going to take a look at what happens when we drive systems near characteristic modes, and then we're also going to look at some low-pass system behaviors. So let's go ahead and take a look at this idea first of driving a system with an input that is near or matching a system mode. Okay. The basic conclusion here that we'll see is that the closer an input is to a mode, the stronger the response is. If I drive a system near one of its characteristic modes, the system responds strongly. There's a kind of a well-known story that many of you, I'm sure, have heard. This idea that you could take a crystal glass, right? A crystal glass. In fact, you might have done this when you were stuck washing Thanksgiving dinner dishes or something like that. You have a crystal glass. You put a little soap on the rim and you rub your finger on the rim, and that thing starts humming, right? It hums at a particular frequency. That crystal glass is very uniform in its structure, and it has a very strong characteristic mode. So we could actually do some kind of system analysis on that. We'd find it has a pretty strong characteristic mode, whose rate of oscillation, right, is dictated by that mode's location. So what was the story? Well, the story is that if you had an opera singer who had a very pitch perfect voice, right, who could sing at exactly that same frequency as the glass, what should happen? Well, that glass will end up responding strongly to that input that is very near its mode, and the glass breaks, right? It induces a resonance, what is called a resonance phenomenon on it, and the glass structure just can't support that new mode, and it breaks. Actually, for those of you who enjoy a little TV, there's a series that's a little bit dated now called Mythbusters, and they actually treat this exact story, and they do show glasses breaking with resonant conditions by singing, if you will, at the glass's frequency. We just want to get a mathematical idea of this. There's many, many other cases of resonance. There are bridges that sometimes have resonant modes, and if you get near that resonant mode, they break. We talked about that earlier in the semester as well. The Tacoma Narrows Bridge back in the early 1900s had that problem. It was designed unintentionally with a resonant mode, or a mode that was near something that naturally happened, the wind, and it caused the structure to respond strongly, and it broke. You can Google that as well. Very interesting video. This has happened even in more modern buildings. Modern buildings, a lot of what engineers do in these tall skyscrapers is they're very concerned about designing structures that avoid having modes that might be naturally activated, right? Whether through wind or maybe a seismic event like a earthquake or what have you. Okay, so let's take a look at the problem. We know a linear time invariant system's output is just the input convolved with the impulse response. We are going to go ahead and look at that impulse response. We know the impulse response depends on characteristic mode, so there's going to be some characteristic mode-like terms inside that impulse response. It's just part of it. If you remember h of t, right, has PD acting on y0, and y0 is made up of characteristic modes. So there's going to be a term in there that has some dependence, direct dependence on the characteristic modes. And what are we saying? We're saying that the input x of t is going to also have a mode, right? And I'm going to let that mode, right, have a characteristic root, or a frequency, if you will, lambda minus epsilon. And as epsilon becomes tiny, right, then that inputs mode starts getting really, really close to the system mode. And I'm just curious what happens on that. If I go through the math on that, if you go through that convolution, I don't care about the rest of the plus pieces. Linearity of convolution lets me handle each piece separately, right? So I can just deal with this first piece. I know there's a bunch of other pieces, but I'm just looking at what happens for the part of the input that is getting close to that part of the impulse response where the modes match. If you go through that convolution, what you find comes out of that is you get an a e to the lambda t, and then you get a 1 over epsilon times the quantity 1 minus e to the epsilon t, and then it's causal because both of the inputs were causal, u of t. Look at what happens as epsilon gets small. Because I have a factor here, 1 over epsilon, as epsilon gets small, right, 1 over a small number becomes really big. And so whatever comes out of there starts growing and growing and growing, and it gets really big. So as my mode gets close, or my input gets close to a mode of the system, right, the response starts getting larger. We can also look at this at what happens in the limit. If epsilon equals 0, that means that my input, right, has a mode that exactly matches one of the modes of my system. This is a condition called resonance. So if you see resonance in a system, it's because you're driving the system at one of its natural modes, okay? And we can take a look at that as well. We're looking at the limit of that output as epsilon goes to 0. That's a limit of at least that part of the term that we looked up there. There could be some other stuff. We're just worried about this one. And what do I see? Well, let's take a look at that right-hand part. As epsilon goes to 0, right, 1 minus e to the epsilon t. As epsilon goes to 0, I'm going to get 1 minus e to the 0. That's 1 minus 1. That's 0. And so I'm going to get a 0 over 0. That's a 0 over 0 indeterminate, at least in its current form. So you know from calculus that you can use L'Hopital's rule, and L'Hopital's rule will tell you what happens to that term in the limit. Well, I bet you can guess what happens to this term in the limit. We had already seen the case before of what happens when you have a repeated root, right? When you have a repeated root, if I had an e to the lambda t and I repeated it, what did we say before we got? We said we got e to the lambda t multiplied by a t. Well, no surprise at all. When I look at this case of not repeating internally, but repeating the root essentially by applying an input that has that same mode, that resonance condition, 1 minus e to the epsilon t by epsilon in the limit as epsilon goes to 0 is easily shown through L'Hopital's rule to be t. So we get exactly like what we would have expected by repeating that root, right? We get a new mode, right? That's resonance. And that new mode looks exactly like the stuff that we talked about before. We didn't derive it before, but this is the elements of the time domain derivation. So that t or t squared or t cubed term, depending on how many times you repeat it, should make a little more sense as to how it comes up and why it takes that particular form. A couple of things to note, and we'd already seen this before when we were talking about stability as measured from the characteristic modes, this idea of internal stability. If the real part of our characteristic root is less than 0, then even if I do resonance, where I get that new mode t e to the lambda t grows, but e to the lambda t decays, it still ends up going to 0 as t goes to infinity, because exponential decay always beats polynomial growth. All right, intuitive insights for low-pass systems. I'm going to ask you to read section 2.6 in the book. I know many of you are reading as recommended. A few of you might be reading a little less diligently. I think that section 2.6 is just excellent. It probably is going to do a way better job than I do in the lecture here, so just give it a read. It's a really nice section. The first part of this section, or in fact almost all of the section, is looking at behaviors of low-pass systems. And so we're going to need to think a little bit about low-pass systems. The first thing it considers is something called the time constant. A time constant of a system is really just how fast the system responds. So if I do a quick change on an input, like I apply a unit step function, for example, right? You apply a unit step and you run it through the system. How long does it take that system to fully respond to the unit step? That's the idea of a time constant to this system. So one of the ways we can measure the time constant of a system, how fast it responds, is by figuring out the effective width of the unit impulse response function. Why is that? Why does that make some sense? Think about what we have. If I have an input that is a delta function, so here's my delta function going into my system, right? And then out comes something. Here's the something that comes out, right? That delta function is instantaneous, right? And then what comes out has some particular effective width, some area where it's mostly non-zero, right? And it has a big bulk of output, a big bulk of output. That is related to this time constant of the system, how long it takes to respond. Instantaneous input, how long does it take for that instantaneous input to transverse or go through the entire system? The way we're going to end up doing it, and by the way, all low-pass systems will have what I'm going to call blob-like unit impulse response functions. So for example, a unit impulse response function that looks like a little pulse is low pass. A unit impulse response that looks kind of like that guy is low pass. A unit impulse response that kind of looks like this triangle-y looking guy is low pass, okay? A unit impulse response that looks like this is not low pass, it's not blob-like, okay? Low-pass systems will always have blob-like unit impulse responses. So it turns out that we can well approximate that blob with a, let's call it, near equivalent rectangle. And the way we're going to get equivalence here is that whatever our unit impulse response is, okay, there it is, we are going to make a semi-equivalent, is an equivalent in a couple ways, approximation to that is rectangular. What are we going to do to make them roughly the same? Our original had some peak amplitude. We're going to make the peak amplitude of our approximation the same thing. Our original had some particular area. We're going to make our approximation have the same area. And when we compute that area, when we figure out how do we make a rectangle essentially have the same area as our original function, the one thing that I can control is I control its width. And that width, th, is the time constant of our system, right? It's the equivalent width, right, of our underlying impulse response as approximated by a rectangle approximation, right, to that low pass impulse response, which is always blob-like. So we can get a calculation on this. We can get the time constant for this guy. It's just the area of the original divided by its peak amplitude. You can get that as the integral of h of t, right, divided by h max. As an example, I could have an impulse response. This is a low-pass system, first order low-pass system, h of t equaling e to the lambda t ut, where lambda is just some real and negative constant that has some sort of decaying exponential. It's effectively blob-like. What's its effective width? What is its time constant? Well, in this particular case, we could see that its peak amplitude is at t equaling 0, so e to the 0 is 1. So I'm going to just get 1, so I'm going to just be dividing by 1. You're not going to see that. And then I need to find the area of that h of t, so that's an area of that exponential function. That's an easy calculation to do, and it's going to be minus 1 over lambda. So for example, if lambda was equal to minus 1, we would find out that the time constant was 1 over minus 1 would just be equal to 1. A system that has a characteristic root at minus 1 has a time constant of 1 second, right? The larger, in this case, that lambda becomes, the smaller is the time constant, right? And vice versa, something along those lines. Okay, so how might we use this and how might we prove this for ourselves? One of the reasons we do this is just because rectangles in general, that rectangular approximation to our low-pass filters impulse response, are just easier to do kind of back of the napkin, quick calculations about system behaviors. And so we're going to see that as we go along here. Instead of dealing with this infinite complexity of different low-pass filters, impulse responses, we're just going to look at their rectangular equivalent to get kind of a first-order quick approximation to what these systems are doing. So we see that in this next concept, this idea of rise time. How long does it take a system to respond to x of t equaling u of t? The rise time of the system. So I apply a unit step input, and I want to know at what point does the output start looking like that unit step. Well, if I've approximated my input as that rectangular approximation, I call that h hat. That's a rectangle whose width is the time constant of the system, th. I convolve those guys together. That convolution is easy, right? We know that we're just going to get a ramp going up before it finally plateaus out, and the width to where that ramp ends is th. So we can easily see here that the rise time of my system is equal to the time constant, and that sort of makes sense. The time constant tells us how quick the system is, right? The rise time, you aren't going to rise up to the full value until you've had a chance to be as quick as you can be, which is the time constant of the system. So rise time is equal to the time constant of the system. We can also use this time constant to understand filtering. Again, the book here, I think, does a really nice job of describing this as well. Basically, these were all low-pass systems. So low-pass filters have a cutoff frequency. That's a place where before the cutoff frequency, they let things through, and after the cutoff frequency, they basically kill the input. They get rid of it. And it turns out that low-pass filter's cutoff frequency is just the reciprocal of the time constant. It's 1 over th. So if you have a really small th, right, your cutoff frequency is going to become bigger. In other words, if you have a really fast system, right, it's going to have a high cutoff frequency. If you have a really slow system, right, it's going to have a lower cutoff frequency. Here's one way that you might get some idea about that. Let's say that we're looking at an input frequency that is much faster, right, than the width of my impulse response function. So I get a lot of oscillations over that interval th. If I wanted to think about what the output of that system is, I would take that sinusoidal input, I'd run it through the system, so that means convolve it with the impulse response, which we approximate as this rectangle. Notice what we get here. We get a sinusoid, right? That's going to get flip and shifted in and run through this rectangle, which is a lot wider than all the oscillations. So I'm going to have all these oscillations when I do that flip and shift going through there. I'm going to multiply those together, so I'm going to get many, many cycles of that sinusoid, and then I'm going to integrate it. Well, that's going to give me some positive sides, right? We're going to get all those positive areas, and then we're going to get a bunch of negative areas. And those guys are going to be pretty close to the same number, right? You could think of this as 1 times that sinusoid. And if I integrate a sinusoid over many, many cycles, right, all the positive cycles area is going to cancel with the negative areas cycles. And that means that the output is going to be small. So if your width, right, is big enough to hold lots of cycles, you're going to get a small output. If instead, right, your oscillations are much slower relative to the width of my impulse response, here I've shown it that you've got this slow sinusoid coming in, and it's getting convolved again with a rectangle function, but that rectangle function looks relatively skinny, right? That almost looks like a delta function. And we know what happens when you convolve something with a delta. You just get that same thing. Output becomes basically input. That means that sinusoid is going to pass, right? It's going to go through basically undistorted. It's going to come out just as strong. Where is the transition? The transition occurs, right? The transition occurs roughly when you have that unit impulse response approximated by a rectangle and an input that has a single cycle in there. Think about what happens on that. If I did the convolution there, that product area is going to go to 0. So that's the first time where you're going to have the positive cycle cancel with the negative cycle. Well, if I've got 1 cycle per that TH, that's a frequency 1 over TH. That's how we got that cutoff frequency. Pulse dispersion. This is an interesting phenomenon as well. Low pass filters are found everywhere. Basically, all practical systems have some element of low pass character. If you think about computers and computer buses, we're interested in communicating information all the time on these computer buses. So we send a bunch of digital information, oftentimes pulses down these wires, and those wires do have some low pass character, right? And so we know that there's some distortion that can occur to these bits that are being communicated on our computer buses. So things like pulse dispersion are really important for us to understand when we think about things like computer communication. So what is pulse dispersion? Pulse dispersion basically says if you're sending a pulse, right, we're communicating some digital information, for example, we're going to let it have some width tx, and you run it through a low pass filter, and we said, hey, let's just do a first order approximation of that low pass filter by looking at it. Its impulse response also is a rectangle function, right, and it has some width th. When I run it down there, what comes out? Well, this is again a convolution that we looked at, and that's really easy. A convolution of two rect functions is a trapezoid, right? And the overall width is the sum of the two widths. We know that through the width property. A couple of things to notice here. The original really sharp edges of my bit, right? Those sharp edges, what is a sharp edge? Rapid change in voltage, rapid change is high frequency. They got softened, right? They ended up going to a slope rather than that discontinuity. The edges are not as sharp. We expected that, right? This is a low pass filter. It passes the low frequencies. It does not like high frequencies. It doesn't like rapid change. It needs to soften those. And to soften those edges, it needed to widen things out. So the pulse ends up getting dispersion in there, pulse dispersion. It ends up getting wider by an amount th. Why is this important? Well, if I'm trying to send these bits, consider the following case, right? I've got a bit sequence that I want to send, 1011. So I, as a designer, can design some bits so that I can send 1, 0, and 1, 1. I'm going to do it by sending as skinny a bits as I possibly can. Okay, so I'm going to make these little tiny narrow bits, and I'm going to send a positive pulse for a 1 and a negative pulse for a 0. So I get something that looks essentially like some deltas, some plus deltas and some negative deltas. Because of pulse dispersion, right? Because of pulse dispersion, when I send this through a system that is low passing character, these skinny bits are going to get widened, right? And they're going to get widened according to that triangular impulse response. So take that triangular impulse response, right, and convolve it with these bunch of delta functions. What am I going to get? I'm going to get some triangle, or some rectangle, some rectangle, some rectangle, some rectangle. A delta convolved with anything is the anything, and the anything here is just that rectangular function. We could see in this particular case, the way I've drawn it out, the pulse dispersion, right? This T sub H, that input delta got widened to, is probably okay because the pulses have not gotten so wide that they interfere with the next pulse over. We would be in trouble though if those input deltas, if those input bits came at a rate faster than TH, right? Because then, because of pulse dispersion, as those bits go through, they're going to start overlapping one another, and that information is going to get mixed up. So because of pulse dispersion, right, we want to space the bits at least TH apart so that the bits after the low pass filter don't overlap. That means our bit rate needs to be, again, less than 1 over TH. So that's the same as the cutoff frequency of our system. If you have a system that has a natural cutoff frequency of 10 kilohertz, right, it's probably going to be suitable for about 10 kilobits per second transmission. And remember what that cutoff frequency is. That's related to that fastness of the system. The faster the system, the higher that cutoff frequency. So if you want to send a lot of bits, you better have a fast system. Really, that's the end of chapter 2. Next time, we're going to go into chapter 3, which does a lot of this stuff all over again, not for continuous time systems, but for discrete time. So we'll fill in some details on discrete time signals and systems, and then we're going to go through and solve a class of system constant coefficient linear difference equations, much like we just did for differential equations.